Okay, now we are gonna try to figure out the maximum torque in our squirrel cage induction machine using our steady state model. So here is to do this, it will be better to do it in our Thevenin equivalent because uh, we have we can find the maximum power if we use the maximum power transfer theorem. And for the maximum power theorem, we need the Thevenin circuit. So maximum power transfer theorem says that the maximum power output is obtained from an AC circuit when the value of the load resistance is equal to the magnitude of the internal impedance of the circuit at the of the terminals of the load. Okay, so here we're gonna have our load resistor RL, and this will be our internal resistors or our internal impedance. Okay, so we know our equation for torque that we found in the last video. That is this. Okay, so to get this torque, we need to find IR in our new circuit. So we know that this is the Thevenin equivalent, so we know that IR is going to be here. IR is going to be equals to these three resistors in series, the voltage over these three resistors in over this all these resistors in series. Okay, so we have that our IR is equals to voltage 1 equivalent over resistors 1. I'm just gonna start calling it R1, and we know that these two are the equivalent impedance and resistance, plus x2 plus R2 over S. Okay, so this is how we get our IR here. And now we can plug this in our equation for our Thevenin, for our torque. So we are gonna have that our torque is equals to 3 over omega synchronous mechanical times our voltage V1. Still, this is the equivalent. Okay, and this is a square, so we need to square all of this. This will be r square, r square is 2. All of this has to be a square. Okay, so I'm just gonna clean it a little bit so we get all our imaginary together. So we have b1 square, we have s1 plus s2 square plus r1 plus r2 over s square. Okay, so this is our IR. So we have 3 over b1 square, and we have, well, actually we have all of this. This is our IR. So let's put it here. Where all of this times R2 over S. Okay. So this is our equation for torque, our developed torque in our squirrel cage induction machine when we use the Thevenin equivalent circuit. Now, let's talk a little bit about power flow in our circuit. So we know that we are going to have our power in, and the first losses that we are going to get are gonna be the stator copper losses. Then we are gonna have the core losses, the core loss. This is loss. So after that, we're gonna get the power in. If we have the power in and we subtract the two, we get the power in the air gap. And then from here we have the rotor copper loss, because the power in the air gap is the power going into a rotor. Then we are gonna have our mechanical losses, and whatever is left is our power in our shaft. Okay, so this is good because if we have our power in an air gap, we subtract the rotor loss and mechanical loss, we get our power in a shaft. So like this we can calculate our different powers. Okay, so now we are going to try to figure out what is our maximum torque. So again, here we have our equation. Now, we said that when we have the value of the load resistance equals to the magnitude of the internal impedance, we have the maximum power. So we know that the load resistance is R2 over S. And here we're going to have the magnitude of the internal impedance, that is the sum of our these three. So this load resistance is the sum of these three. So the magnitude of them is going to be R2 over S square root R1 square plus S1 plus S2 square. And so this is our maximum power. So our maximum slip is going to be, or our slip when we get our maximum torque is going to be R2 over this. And now we can figure out the formula to get the maximum torque. Okay, to do this, we are gonna need to take our equation for torque, and wherever we see x, we now put this value. So we are gonna get this. Wherever we had x, we put the value we figured out, or the x max. And now we can say that R2 over R2, well, this value over here, this value is equals to R2 over R2 is equals to just this. Okay, so now we can change our equation, so it has this. And here we have it. Whenever we had this, now we have R squared. And now what can we do? We can collect this with this and put this on top. So we are going to have this times this. multiplying this. Okay, and now down here we can say, well, we can do much with this term, but we can expand this one. So we are gonna get r1 square plus 2r1 and all of this plus this one square, and this one square is just this without the square root. Okay, and now we can collect similar terms. We're still gonna have this here, and down here we can collect the ones that are equal. So we're gonna have 2 this plus 2 of r1 square, this one and this one, plus 2r1 times r1 square plus h1 plus h2 square, and all this divided by this. Okay, now we can take the 2 out. So we can say 2 here because it's in h1, and we can collect the so we can collect the 2 out, and we can put together this over these two. So we are gonna have r1 square plus this. We're gonna have plus this one over this one plus r1 over this. Okay, now if we have a to the square root over a is the same 1 over a over square root. So that's what we have here. So we have 1 over square root, so we're gonna have this one, and on this side here these two terms are equal, so it's 1 over this two. So we are gonna have, when we join them together again, 1 over this square root plus r1, and this is the equation for our maximum torque. So how is this graph gonna look? Something like this. Okay, a little smaller. So here you can see the slip is this one. So the smaller the slip, the bigger the torque. But you can see that when we get a slip of 100%, the torque is 0. This happens because, as we talked in a previous video, the synchronous speed if we have the synchronous speed, not the sleep, just the sleep speed is equals to the sleepy mechanicals minus the speed in electrical. So if these two are equals, it's zero. But also another way of saying is that we have the two magnetic fields rotating, and the EMF is equals to the velocity times the magnetic field, the flux density times the length of the conductor. So here we are going to have the multiplication of the magnitudes times sine of theta. So if theta is 0, this whole thing is 0, so we don't have EMS induced. So if we don't have EMS induced, there is no current in the rotor, and if there is no current in the rotor, there is no magnetic field, so there is no rotation. Another thing that we can say here is that we have over here the equation for our torque. And this is multiplying, I don't know what color, for example, R over S. So this black one is in a certain R. Let's say this yellow one is R1. Okay. So what will happen if we use instead of R1 a bigger R2, a resistance R2 here that is bigger than R1. So if we look at our equation for the maximum torque, and we don't see here this R in this equation. So this maximum torque is gonna stay the same, but this whole value is gonna start bigger, because for example, if we have 0.2 and R1 is 10, we will get like 50. If it is 100, then it's gonna be 500. So we're gonna start with a bigger value of torque. So here we have our TD. This won't change. So the graph is gonna be the same, but we start with a bigger. And again, it has to be 0 and 100% because what we just discussed. So if we change this resistance value, oh well, that was the yellow. Now yellow, let's make another blue. If we change the resistance value, we can change the speed of the motor, the induction machine, but this will require us to actually change a resistor in a moving machine. So it's not practical, but this is how we can calculate the maximum low torque for our squirrel cage machine using our Thevenin equivalent of our steady state model. Hope this helps.